So the standard cell potential for any electrochemical cell depends on which half reactions are occurring. And that it's a measure of the potential energy difference between the two electrodes, like the difference in elevation between the head of a stream and the end of it. So we can think of each electrode, we can think of the electrode in each half cell as having its own potential. And so here, I guess you could say this is like elevation, right? You've got the elevation of the head of the stream, you've got the elevation at the foot of the stream, and we're looking at the difference in between them. So that elevation or potential is called the standard electrode potential. So this is the potential for one half reaction, as opposed to the cell potential, which is for a combination of two half reactions. So the standard cell potential is the difference between the two standard electrode potentials, just like the difference in elevation is the difference between the elevations of the two parts. And here's the picture with the water tanks again. So here, this water is higher, it has a higher potential energy, it's elevated above the level of the water in the other tank. So this is the water's then going to move from high potential energy to low potential energy. When we have two half cells connected, the electrons are going to go from the one with the more negative charge, which is the greater potential energy, to the electrode with the more positive charge, which is less potential energy. So again, they're going from high potential energy to lower potential energy. What gets a little confusing here is that negative is greater potential energy here, not positive. Why is that? Well, let's think about it. The electrons are leaving the anode, right? If the anode is positively charged, are the electrons going to leave? No, they're not going to leave. If the electrode is negatively charged, the electrons are like, we got to get out of here, right? They're going to move away. The more negative that charge is, the more the electrons are going to move away. Okay, so we've got it, kind of a cross of positive minus here. So we can't measure the electrode potential in a half cell directly. And so we chose a 0 point. Much like with elevation, we decided an easy thing would be to measure it relative to sea level. So we say sea level is 0 elevation. We're going to say that this standard hydrogen electrode is 0. And we're going to measure everything relative to that. So we've got this one half cell that's assigned a potential of 0. We measure everything else relative to that. The standard hydrogen electrode is hydrogen ions being reduced to form hydrogen gas. Okay, and so that has a an electrode potential of 0 because we decided that. This is what a standard hydrogen electrode might look like. And here, this has to be standard potential. And so here we have 1 molar H plus ions in the solution. And this is in the presence of 1 atmosphere of hydrogen gas. We need an inert electrode here to attach a wire to so that we can have the transfer, because these things are both not solids. Any questions? These electrodes are not super convenient because you have to have hydrogen gas at a pressure of 1 atmosphere, but we don't use them very often. They were just used to measure everything else, right? And so then everything is measured relative to this, but then we don't need to use it anymore. So this is how you would measure a half-cell potential with the standard hydrogen electrode. So this side is the standard hydrogen electrode, and over here we have that zinc oxidation reaction. So when we connect this zinc reaction to the standard hydrogen electrode, and if we measure the voltage difference between the anode and the cathode, we get a number of 0.76. So this is the cell potential. The cell potential is the difference in voltage between the cathode and the anode. The anode is the initial state, the cathode is the final state. So E cell is final minus initial, or E cathode minus E anode. So if this is 0, so what we've got here is E cell is equal to 0.76, which equals E for the anode. Nope, sorry. That's the cathode minus the anode. And here the cathode is 0. And so we can calculate the potential of the anode, right? So the potential for that zinc reaction is negative 0.76 volts. Because 0 minus negative 0.76 is what gives us the positive 0.76 that we see here. Because this electrode, we decided would be 0. So we measure everything relative to the standard hydrogen electrode. So, you can hook up any of these different half reactions, you can hook it up to this, measure the potential, and from that you can tell what the potential of the other half reaction is. And like I said, we don't go around doing this all the time, but this is where these numbers came from. It's how they figured out what those numbers are. Any other questions? Oh, yeah, I just drew this, and here it is on the slide. So the measured cell potential was positive 0.76. That cell potential is the potential at the cathode minus the potential at the anode, because it's a difference in those potentials, right? So E cell is 0.76. The cathode is the standard hydrogen electrode defined as 0 minus the anode, and so the anode ends up being negative 0.76. The more negative electrode potential means greater potential energy of an electron at that electrode, because negative charge repels electrons. So this being negative says, oh yeah, the electrons are going to want to move away from that. And so really you've got a competition between the potentials at the two electrodes. And the electrons are going to flow to whichever one is more positive. For the copper ion electrode, if we measure the cell potential versus the SHE, it'd be negative 0.34. So this has a more positive potential than the standard hydrogen electrodes, which means it has a lower potential energy for the electrons. So things are going to go from high potential energy, more negative, to low potential energy, more positive, because the thing that's moving is a negatively charged electron. So the electron wants to go away from the negative and towards the positive. So because the anode here would be at a more positive voltage, the electrons are not going to flow to the cathode. They're actually going to flow from the cathode back to the anode. And so we've got the anode here being positive relative to the standard hydrogen electrode. The more positive the electrode potential, the lower the potential energy of an electron at that electrode, because positive charges attract electrons. So this copper electrode was positive relative to the standard, 0. So it's going to draw electrons away from the standard hydrogen electrode because it's positive relative to that, and so the electrons are going to go towards it. The zinc electrode is negative relative to the standard hydrogen electrode, and the electrons are repelled by that negative charge, and they're going to move towards the standard hydrogen electrode. So by convention, we list standard electrode potentials for reduction half reactions. So reduction is gain of electrons, and so here we have something gaining electrons and forming something else. These are all going to be listed as reductions. So the reduction reaction for this is positive, the reduction reaction for this is negative, because they were measured against Xi. So the way the book teaches it is that the cell potential is the cathode potential minus the anode potential. So let's go back and look at this and calculate what the voltage for this, or this cell potential for this would be. So we had the zinc on the left. The zinc was the anode. Oxidation occurs at the anode, right? So this was the anode. Whoops. This was happening at the anode, and this was the cathode. And so the cell potential is the potential of the anode minus the potential of the cathode. No, the opposite. So the cathode is positive 0.34, and we're going to subtract the anode, which is negative 0.76, and we're going to get so 0.34 minus negative 0.76, 1.1. That's the way the book talks about it. I find that very confusing. You see, I got things backwards a couple of times in there, right? Even just talking out loud to myself, and I'm teaching this stuff. We need to identify which one's the cathode and which one's the anode, and then remember which one to subtract from which in order to get the correct potential. So, Mrs. K's thoughts. You can do that. The reduction potentials are listed in table 20.1. It's a pretty extensive list. Or, this is how I think about it. You can add the half reactions and then add the cell potentials. So one of these is going to be an oxidation and one's going to be a reduction. So this is the reduction. Let's see, I think I did this. No, I didn't. Okay. So we had in that picture, here we had the zinc in the anode position. The zinc was being oxidized. So instead of identifying which one of these is the anode and which one's the cathode, what I prefer to do is we're going to have one oxidation and one reduction. These are both written as reductions. So this one is going to be the oxidation. I'm going to write it backwards. I'm going to write it as an oxidation. If I change the direction, yeah.
Do we know which one should be the...
That's a great question. It can be hard to know. I'll talk about that in just a second. So if I switch the direction of this, then the electrode potential is going to be flipped, right? It's going to change sign. So for this, it's plus 0.76 volts. If you go one way, it's positive. If you go the other way, it's negative, right? This is a lot like delta H, right? You reverse the reaction, you change the sign. Here, you reverse the reaction, you change the sign. So we're not using this one. And now we're going to add these two equations. We see the electrons cancel out. And the cell potential is the sum of those, which is positive 1.10 volts. What if I chose the wrong equation to write backwards? I'm going to get a negative cell potential. Does a negative cell potential mean a spontaneous reaction? No. The cell potential has to be positive for it to be a spontaneous reaction. So if I end up with a negative cell potential, I know I just need to flip everything the other direction. Okay? Just flip it around. You don't have to do any calculations. You just write this backwards and change the sign on that guy. I think this is a lot easier than cathode minus anode. So then looking at this one, we could guess which one. This one, because we've got 0 here, we can kind of see that, well, if we add these, this is going to be a negative. Changing the sign of this one doesn't matter. I want this to come up to be positive, so I'm going to change the sign on that one. I'm going to write this one backwards. So the electrode potential is plus 0.76 volts for that one. I'm not using that anymore because I reversed it. And then when I add these together, the electrons are going to cancel out. And the cell potential is plus 0.76 volts. One thing that's just a tiny bit different than with delta H's, you do not multiply the standard potential by a coefficient. We've got 2 electrons here. We're not going to multiply the electrode potential by 2. We'll see that multiplication thing comes in a different form. But here we just flip them, change the sign, add them together, done. So this is the table in your textbook that has all of these reduction half reactions. There's a whole bunch of them, and this isn't even all of them. And so when you are looking for ones in here, you need to be careful because here we've got permanganate ion in two different ones. One, it's going to MnO2, and the other one is going to Mn2 plus ion. And so you have to make sure you choose the correct one. So at the top are the ones that are most likely to be reduced. So, relative to the standard hydrogen electrode, these are positive. So here, these like to be reduced. Then if we go to the bottom of the table, so here we have the standard hydrogen electrode in the middle is 0. And then down below this, they're going to have negative potentials, which means that these reactions would normally want to go as an oxidation. They would normally be reversed to get a positive cell potential. Okay, so summary slide. Electrode potential of the standard hydrogen electrode is exactly 0 because we decided that. An electrode with greater tendency towards reduction is going to be positive relative to that. An electrode with lesser tendency towards reduction is going to be negative. The cell potential is the difference between the electrode potentials of the anode and the cathode. The standard cell potential is going to be positive for spontaneous reactions. It's negative for non-spontaneous reactions. Use tabulated standard electrode potentials to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees Celsius. The equation is balanced. Okay, so here we have the balanced chemical equation given to us. We don't need to decide which is the reduction, which is the oxidation. We're just going to use it as it's written. So this is like when we were balancing. We're going to break this into two half reactions. And we don't need to worry about coefficients or numbers of electrons here. And we don't need to know, are we oxidizing or reducing? We don't have to think about any of that. So when we were balancing, what we would do is we'd just take the first one, Pb2 plus, aqueous, and then the product would be the product that looks most like it, right? Pb solid. And then chromium and chromium-3 are the other ones. Put some electrons in here. So this is a positive charge, and that side's 0. This is the part that's gaining 2 electrons, and this one is losing 3 electrons. This is like the first step in balancing half reaction method. Make the 2 half reactions. They're balanced individually with their electrons. Okay? We're not trying to balance this so we don't have to go and multiply or do anything else. We're just going to look these up in the table. So this one is the reduction, right, where it's gaining electrons. And so when we look in the table, we're looking for lead-2 ion. Here's lead-2 ion plus 2 electrons to make solid lead. So this is the way the equation is written, and so we're just going to copy down the cell potential for that, negative 0.13. So I found this, it matched up exactly with what was in the table. I write down the same number that was in the table. Now we're going to go looking for this one. We're not going to find it in this direction. We're going to find it flipped in the table, but we can still find it. So let's go back and look for that. We've got solid chromium on the one side, and we've got chromium 3 plus on the other side. So what I have is this equation written backwards, right? So I'm going to take the potential for that reaction and do what? Change the sign, because I'm looking at it backwards. So instead of negative 0.73, I'm going to write plus 0.73. These are the two half reactions. To get the cell potential, I add these together. And I get plus 0.60 volts. So I think this is a lot easier because I did not really have to identify what's at the cathode, what's at the anode. So I knew which to subtract from which. I didn't have to remember that it was cathode minus anode. Somehow that's just something that will not stick in my brain. I'm going to take my equation, write the two half reactions. One of them is going to be an oxidation. One of them is going to be backwards of what I see in the table. So I find it in the table and I just change the sign on it. And then I add things together. Done. So is this a spontaneous reaction? Could this be used to generate electrical current? Yeah, because the cell potential is positive. Any questions? I don't like that question, so we're not going to talk about it. Predicting the direction. You're comparing the potential for each half reaction. And so this, again, is the way the books is thinking about it, right? But the more negative one tends to lose electrons, that's going to be the oxidation. The more positive one tends to gain electrons, that's the reduction. In a spontaneous reaction, the cell potential is positive. So how can we predict this just looking at the table of what two things will be make a spontaneous reaction? Let's go back to the table here. Well, let's start at the top. So the numbers are large positive going smaller towards zero, and then they become larger negative, right? So if I have one of these being positive and the other being negative, if the positive one is above the other one, then I'm going to have a positive cell potential, right? So let's just choose a couple at random. So if I'm combining those, so the reaction that's reduction needs to be above the oxidation in the table, because we're going to flip one of them backwards. That one's going to become negative. If you take any of these that are below that and make them negative, when you add them together, you'll get a positive number. So here, predicting the direction of spontaneous, or the spontaneous direction. Here I've got two reduction reactions just pulled out of that table, right? Okay, so what am I going to do so that when I combine these, I get a positive number? If I switch the sign on this one, then when I add it to that one, it'll be positive. So I'm going to do this, Mn solid to Mn2 plus 2 electrons. I wrote it backwards, so I changed the sign. When I add these together, I get a positive number. Whoops. Plus 0.95 volts. So the manganese is going to go to manganese 2 plus. That's going to be losing the electrons. So this is the one that's losing the electrons. The electrons are going this way towards the nickel. If I picked wrong and got negative 0.95, I've not really wasted any time. I just realized, oh, I got it exactly backwards, other way. Any questions?
Yeah. So we are switching the one to get the cell positive.
Mm-hmm.
So we are aiming for spontaneous reaction.
Right.
Do we always have spontaneous reaction?
You don't always have spontaneous reactions. What we'll see is you can make a non-spontaneous reaction happen, but you have to drive electricity into it to force it backwards.
So how would I know that the A cell should be negative?
Well, you're gonna be given a reaction and asked to calculate E cell. And so you're gonna do that like we did this one, where you just pull it apart, the directions are already set, okay? The other thing that can happen is they might give you like these two half reactions and say, well, what direction is the spontaneous reaction? What would be at the anode, what would be at the cathode? Here they gave us a picture, so we could have also just looked at the picture. But here we're gonna combine, we wanna flip one of these and combine them so we get a positive. And so then our reaction is Mn plus Ni2 plus, going to Mn2 plus nickel. How do we identify which one's at the anode if we're supposed to be drawing a picture of this? Oxidation occurs at the anode. They both start with vowels. Reduction happens at the cathode. Red cat. So then I look at these, okay, which one's the oxidation, which one's the reduction? And then I think oil rig. So oxidation at the anode. So on this side, I'm looking for the oxidation. I'm looking for the thing that's losing electrons. That's this guy. So this would be at the anode, as it's shown here. And the other one would be the cathode. The whole positive negative thing can be very confusing. But the good news is if you do it backwards, all you have to do is switch everything. Flip the direction, change the sign, you're all good. Any other questions? Okay, so this one's a little bit tricky because they've cut off the cell potentials over here. These are all reduction half reactions. And so if we take one of these in the forward direction and add anything below in the reverse direction, it will be a spontaneous reaction. So this is saying, sketch the electrochemical cell in which the spontaneous reaction would occur, label the anode, the cathode, and the direction of electron flow. Well, let's look at what we've got going on here. You could look at this without pulling them apart, but I'm going to pull them apart. So I have zinc going to zinc ion, and I have nickel ions going to nickel solid. So I need 2 electrons over here and 2 electrons over there. Well, which one of these is the reduction? Which one matches with the electrons on the left? Right, it's the nickel. So let's find the nickel one. There it is. And then the other one is the zinc. Let's find that one. This is the one that's shown in the forward direction. If I then take anything below it and flip the direction and change the sign, I don't need to know what the numbers are. When I add them together, it'll be positive. So this is spontaneous in the direction as written. And so this is the reduction. Oops, that doesn't work very well. This is the reduction. This is the oxidation. Oxidation happens at the anode. Reduction happens at the cathode. This is one of the few things that I might ask you to draw on an exam. Normally I avoid drawing because, well, a lot of us are not good at drawing. But it doesn't have to be beautiful, I just need to understand what you mean. And then we have our light bulb here and our wire going from one side to the other. The anode is always shown on the left. The cathode is always shown on the right, in alphabetical order. So oxidation is happening at the anode. The anode is over here. That means this side has the zinc and the zinc ions. So this is going to have zinc ions in the solution, and this is a zinc metal electrode. The other side is going to have nickel ions and a piece of nickel in it. So I've labeled the anode and the cathode. Anode and the cathode. What direction are the electrons flowing? They're going to the cathode. So the electrons are going this way. So when you draw this from the right perspective, the electrons are always going from left to right, just the way we read. Anode to cathode, alphabetical order. There it is. Any questions?
Does it matter if you say the anode is it the solution or the metal?
Well, that's a good question. Is the anode the metal or the solution? So there is a reaction occurring at the anode. And there's a reaction occurring at the cathode. So the cathode is the piece of metal. The anode is the piece of metal. If you have one where everything's aqueous, then you might have a platinum wire in here. That would be the cathode. But the reaction occurring at the cathode is the reduction half reaction. So the reactions occur at the electrodes, which is where the electrons can get transferred to other things. And the electrode is, if we have a metal, then the electrode should be made of that metal. But if we've got Cu2 plus going to Cu3 plus, whoops, that's really bad. plus an electron. Okay, so this is a half reaction. This is an oxidation reaction. So that might be happening at the anode, but what is the metal going to be, the actual electrode? Well, we can't have copper in there. That's not one of the things. So we're going to put something inert, like platinum.
And the platinum will be the anode.
Pardon me?
And the platinum will be the anode.
Yes. Yeah. So anode and cathode refer to the actual electrode, but they also refer to the side of the cell. Yeah. Any other questions? How about this one? Is this spontaneous under standard conditions? You're not going to make us draw it. Well, what we want to do is we want to find the half reactions in the table. We could write them out, or these are, relatively simple. We've got zinc and zinc 2 ion. Well, let's find one. Where'd you go? Here. This has zinc 2 ion and zinc, right? And the other one is calcium 2 and calcium. So let's find that one. That one's down here. So for the reaction to be spontaneous, this one needs to happen as written, and this one needs to be backwards. Is that what we have going on here? No, it isn't. But let's write it out just so it's easier to see. So we have zinc solid going to zinc aqueous plus 2 electrons. And we have calcium ion plus 2 electrons going to calcium. So this one matches that. This one is reversed. Here's a weird analogy. So you and a friend are moving a desk, right, through a doorway. Somebody has to walk backwards, right? Do you want to be the person who walks backwards? Not really.
Barely walk forward.
I know, you can barely walk forward. So this is like a list of who's stronger, who gets to walk forward, and who gets to walk backwards. So the one that is higher gets to walk forwards, and the one that's lower has to walk backwards. So that says that we're going to switch this, reverse it, in a spontaneous reaction. We have the opposite here. Is it spontaneous? No. Any questions?
Can I have $1 million?
No, sorry, you cannot have $1 million. Okay, we're going to stop there.